Yeah.
Because can't we just post it on the main?
On the main, yeah. We could also post
I mean,
the
because
link.
you're doing it
Here.
live, right? So you should let people know.
And one comment, so under the comment it was.
Okay, yeah, no, that's scary.
Yeah.
Okay, hey, wait. So, but I can share it.
Yeah,
right?
maybe share it then.
Interview for what?
No, it just looks like that, but it's not true. So he helped to fix that. So yeah, how are you?
Yeah, good. Today it's basic electric.
Yeah, so I'm gonna
What do you want to do?
So hello again. So this is the next edition of the Fab Academy Thursdays. So we renamed it to Thursdays, and I think we are going to follow it as Thursdays because it's the open days at the lab. Yeah, by the way, we are at the AutoFab Lab in Helsinki, as you already know. You found it. My name is Chris, and today we are going to talk about basic electronics, because this week on the Fab Academy the topic is electronics production, and actually the task this week is to produce in-circuit programmer, kind of a simple device that you would use for programming chips. And to make more complicated devices like the Arduino microcontroller board, or controller boards for CNC machines, or controller boards for LED lights.
I learned some basic about the Arduino and then Raspberry Pi, but I forgot almost all.
Okay, so
you start over. Once you start over,
you're here to refresh your knowledge about that. Oh, that's good. Yeah, just I also keep repeating all the time. It's not possible to remember everything and keep it in your head. Yeah, so I'm gonna try to use a few slides to explain the Fab Lab perspective, or my perspective on electronics. So what is electricity? So sometimes, whenever you forget what an electronic component is doing, or what is it for, it's very useful to remember what is electricity, how it works, the basic concepts of it, which is not that difficult in my opinion, and that sometimes helps you to solve otherwise seemingly complicated problems. So what is electricity? So it starts from physics. So in physics, electricity comes from the atomic model, and in atomic model you have like the center of the atom, which consists of nucleus and protons, and neutrons. And then around those there are many electrons spinning around. And what happens that by using different methods, you can make the electrons to leave the orbit. But this is Javi. Well, yeah, he was last year he made like a really interesting thing with with a smoke machine, but that was the previous one, so unfortunately it's not possible to roll back. Yeah, but about electricity. So there were many things. So with different things you can. Yeah, this is distracting. That's true. So there's things that make the electrons leave the orbit, but then in the orbit there's an empty place, and these empty places in the orbits, they are attracting other electrons, or the so-called free electrons that are floating around. And these are very likely to fall into that. And basically electricity is a flow of these electrons. They are jumping from atom to atom, and in a certain direction. And they are not necessarily linear direction, but it just seems to us that it is linear, but it's like a random motion of electrons inside a material, inside a conductor, so to say. So this is how it looks like as yeah, as far as the humans have understood it in the micro level. And in schematics, it is perceived a bit differently. So there are two ways how to look at schematics. If you look at them from the physics standpoint, then you can think of electrons moving through the wire, and they are flowing in one direction, usually from minus to plus. So if you look at the terminals of a battery, for example. But in electricity, like the theory side of it, when you are talking about circuits and PCBs and electronic components, we are talking about current, which is a bit more higher level concept than electrons. It takes into account the number of electrons, but then by using some formulas, it is being converted into amperes and milliamperes, amperes. I think there was a certain number, like 16 million, or there was a number like in millions. How many electrons is actually 1 ampere? And it is the amount of chunks or blocks of electrons flowing through a material in 1 second. So 1 ampere is electrons, like block of electrons flowing through a wire in 1 second. And the theoretical concept of electricity, obviously current, is usually moving, so you should perceive it as moving from plus to minus. So this can be very hard to remember sometimes. So when you're looking at a diagram like this, then you should always think that the current is flowing from plus to minus. Yeah, so prioritize that. So, but whenever you run into problems, or you want to kind of, you see that there is a need to get into the physics layer of it to solve a problem, then remember that actually the electrons, they flow in the opposite direction, but usually, yeah, you should think it like this. And then there are 3 basic properties that describe the flow of electrons or current, which is voltage. This is how strong the flow is, so how strong the electrons are pulled into one direction. Then current, so this is relates to the amount of electrons flowing through a cable or a material in 1 second. And resistance, so which is what is the resistance that the electrons face while moving through this cable. Like, for example, yeah, you could perceive it as you could compare it to the flow of water also. So if the pipes are really large, then there's more water flowing through it, and if the pipes are really narrow, then there's less water flowing, and thus there's more resistance to it. So in a similar way, you could look at current and how the electrons are moving through material. So if the material is smaller, that means that there's less material for the electrons to jump on an atomic level. So there's less flow, and when there's a lot of material, then the electrons just can flow. But then it's a matter of voltage, whether it's enough voltage to push the electrons through. And then there's a very useful law or mathematical, like physics concept, which is called the Ohms Law. It sometimes comes in handy in order to calculate the necessary loads and voltage and current needed to drive a certain component. And it's, yeah, for basic electronics that you are going to do at the Fab Lab, for example, or related to Arduino or Raspberry Pis, this is usually just enough for most of the cases. So V stands for voltage, I stands for current, R for resistance, and voltage is measured in volts. Current is measured in amperes. I didn't write it down here, but yeah, you can, I'll update that. So resistance is measured in ohms. But for now, it might be a bit too much. So maybe you have some questions, and we could discuss this, and then I could move towards showing things on the table.
Not too many.
Was it clear?
One thing that I realized was that the importance of cables, especially when you go to higher power, like if you have too much current going into a thin cable, then it's like it's trying to jam through this little cable, and then there's so much resistance that then the resistance means heat, and it heats up and can start burning. So that's why different devices have different thickness wires, and it's really important to kind of know the basics basically for that, so you don't burn your house down or your device.
So okay, and here we have a table set up. So with a battery. So we have some 3 AAA batteries. So these are AAA, the thinner ones. Which direction is more to the center, like this? I'll move the camera a tiny bit more. So yeah, so these are AAA batteries. Each of them are 1.5 volts. So they have a plus on them and usually a minus. So every battery usually would have a plus and a minus indicated somewhere on the body of it. And what is happening with this battery holder, for example, is that if you insert 3 batteries, then they become chained. And in electronics, it is if you chain power supplies like batteries. So chaining means that you attach the plus terminal to the minus terminal, and then the next plus terminal to the next minus terminal. So the voltages are actually added up like this. And I think, yeah, if you add it in parallel, then the amount of current that you can push out, so the amount of electrons that increases. In this case, how powerful the stream is going to increase, and in this case it's going to be the load. But in our case, in order to drive a basic LED, we'll need a bit more voltage. So let's assume that we'll need, so each of these is 1.5 volts, so combined it will make 4.5. And then we have this one, which is called LED, or if you look behind the letters, then it's the light emitting diode. So this one is red, supposed to be red, and usually these have two legs, so 2 connectors. One is longer, one is shorter. The longer stands for plus, the shorter stands for minus, and which means that the longer one, the plus one, you have to connect to the positive terminal of the battery, and the shorter one, or the minus, you have to connect to the negative one. So, and if you don't use any, so 4.5 volts is not that much. So you can just connect the plus to the longer one and minus to the shorter one, and you see that the LED actually lights up. So I can show you like this. Ta-da! Here it goes, it glows. Related to this, I think I forgot also to add it to the presentation, but what I could explain now is that there are 2 types of current that we would face every day. One is the altering current, which is basically when electrons are moving back and forth in the cable. This is the type of current that we would get from an AC socket, the socket, so the electricity connectors that they have in walls. So it's usually 220 volts AC current, and then there's usually a hertz value which defines frequency. This is how often the direction of the current changes. So if it's 50 hertz, that means that it's 50 times a second the direction is going to change, so the electrons are going to flow there and back all the time. And then there, in the devices that we use on an everyday basis, in the charger, in the power supplies of those, there are usually little circuits which are transforming this altering current into direct current. This is what the batteries have, naturally, ecologically. And this is direct current. It's a constant flow of electrons in one direction, and this is what we usually need in devices, in smaller electronic devices. So these are the two types of current, like altering current and direct current. And in electronics, so the kind of electronics that we are going to talk, like that we are looking at today, it's going to be more the direct, it's going to be always the direct current. And also this mobile phone that I use for checking the stream, it's going to be, it runs on direct current, basically. What else? I think, I could demonstrate some things with resistance, for example, and in order to do that, I'm going to use helper tool, which is called the breadboard. So usually, the solderless breadboard. Solderless meaning that you do not need a solder and soldering iron in order to connect things. And with this, it is, as you can see here, here it is that can I make this? Is it visible enough? Maybe I can just make it bigger. No.
Full screen projector?
It's not the projector. It shows you the thing on a display.
No, not this one.
Can you full screen that? Or is that just this one?
Yeah, this one. Here you can see. Can you pass me the pencil? That one. Yeah. So here you can see that there's a plus and minus on the board. Plus and minus. And there's a red line next to the plus and a blue line next to the minus. And it means that, and then there are these small holes, and in those holes you can put jumper cables, which look like this. These are jumper cables. They have metallic end, open end on both ends. So this one is red, and what you can do, you can plug these cables into the breadboard like this. And if you plug another cable on the other end, like this, in this case on the plus side, that goes along the line, you can consider that these two cables are actually connected. So and then and then these where the blue line goes and where the red line goes, so all these holes here are connected. So of course, like the red ones are connected with the red ones and the blue with the blue ones. And then here you see other ones, they are connected in a perpendicular fashion. So these are connected like this. So if you plug something in here, it is going to be accessible here. So it's going to be connected with the top one here, like this. I will make a short demonstration. So let's use a power source. For a power source, I'm going to use an Arduino this time, not a battery, because the battery doesn't have these. I think it doesn't have nice enough cable endings here. But now I'm facing the next problem that I need another USB.
USB-B?
Yeah, no, just USB-A. I just need a little bit of power. Maybe I'll plug this extender. Maybe you can just plug it into your computer. the other end is somewhere there. Yeah.
Should be in.
Yeah. So yeah, it lights up. So you see the green light is here. So it's powered. So it's powered through the USB connection. USB connections usually provide devices with 5 volts. And we are going to use jumper cables in order to get a little bit of power from the 5-volt pin from the Arduino. Actually, let's use just the 3.3 volts. So 3.3 volts are, so let's see, so they have nice labels here. And the 3.3 volts, this is the reset pin. 3.3 volts is this one here, like this, and then we are going to connect a blue cable to the ground, which is so yeah, in electronic circuitry, minus is usually going to be the G and D ground, and sometimes for voltage you will see that it's going to be for voltage is going to be VCC. Yes, VCC is used for voltage as well. So now, yeah, one is connected to 3.3 volts and the other one is to ground. And then we are going to connect the other ends of those to the breadboard. And let's plug in the red cable to the red side of it here, and the blue cable to the blue side of it, to the minus. And we are going to test it with an LED, and we are going to plug the LED, the longer leg to the plus, and the shorter leg to the minus, just like that, and it should light up as it does. I have to find the like this, and it lights up. Then, in order to demonstrate resistance, I'm going to add first one resistor in a chain. So I'm going to connect it through the minus to a pin right here. So if you take a closer look, then you see, so it's from the minus to one of the perpendicularly connected pins, and then I am going to take another LED and I'm going to connect it from the resistor. So I'm going to add the shorter leg to the resistor and the longer leg back to plus. So like this. Now you can see that it's quite dim. It's just barely on. Compared to the other one. Come on. Yeah. So you see the one is really bright and the other is really dim. I wonder, like, just a bit earlier, I'm not sure about the values of these resistors. So there are resistors that are more powerful, that block more current, and then there are resistors that block less. So I'll try another one, which hopefully is gonna be a bit less resistant.
It's a new breadboard. Something.
Yeah, this is a really old breadboard. It's really hard to connect things here. Okay, and then another LED. Yeah, this is gonna show a bit more. I hope so. Okay, yeah, this works. Okay, yeah, here you can see. So you can see that. So this one here to the right is really dim because the resistor is really strong. Then this in the middle one, so it doesn't use any resistor at all. So it's the full current that the Arduino gives. It is also received by the LED. And then the one to the left here, it is so it is connected through a resistor that is not as powerful as this one. So doesn't have that much resistance. So it's a bit dimmer, but not as dim as the one to the right. Yeah. So yeah, that's pretty much it about breadboards and resistance. And it's also, so if you think of current as the flow of water, it really doesn't matter where you added this resistor, before or after the LED, after the light source, because the current is going to be blocked anyway, and it's going to affect the whole circuit. So if you add it before the plus terminal, it's the same as if you would be adding it after the plus terminal. So the brightness is going to change anyway.
But is it safer to do
I
it
always thought it should be in the plug.
like before the device? Is it safer, like if there's an overload or something?
Adding a resistor before LED is safer for the LED usually, because it limits the current a little bit. So in this case, I'm using 3.3 volts. But for example, if I would be using 5 volts, then there would be a danger that this brighter LED has too much current and it is being damaged. So I'll just try it, because if we destroy one LED, then it's not such a big deal. And now, yeah, I think this is because it's actually being overloaded, so it's dimming out, and then yeah, kind of, I think it has some kind of internal protection. Yeah, so 3.3 volts is kind of all right. But then if you connect it to 5 volts, then I think it's overheating and then stopping to work. Yeah, there's even sound.
Ooh, smoke. I saw smoke.
Oh yeah, there is smoke. So yeah, you see, we destroyed an LED with 5 volts. So this is not really good to use with 5 volts without a resistor. So this was a nice demonstration. So this is why you should always add a resistor when you're using LEDs with 5 volts. So I'm gonna replace. Whoa, it's hot.
It seems like a lot of devices also need a resistor, right?
Yeah, you always should look at the ratings. So what is the maximum voltage, and what is the maximum current that can flow through this device? And this is going to give you a hint about what additional devices around that device you need to use. But yeah, it's just a general recommendation that you should use a resistor. But if we are using 3.3, this was the main reason why. Maybe I can bring it closer to the table, and then it's going to have a better focus also. Like this. Arduino enters the screen. Yeah, this is an Arduino, and with additional features, I'll switch to the screen sharing part. And okay, so it has a nice tunnel now, and what I'm talking about is this user interface. This one. Yeah. So Arduino consists of one main component, which is the microcontroller. Am I showing it here? So yeah, which is the microcontroller. It's here. So this is the main part of Arduino. So everything else around it, it just helps us to work with the microcontroller. So for example, this here, this little device, it's a crystal, so which is giving pulses to the microcontroller, so it can carry out the calculations. This specific one is 16 megahertz, so it's like 16 megahertz. That means like 16 million pulses a second, right? So it means that it can do approximately one operation every 16 millionth part of a second. So it's quite fast, but then the microprocessors, which are usually in our computers, they are much faster than that. Then there's a little USB chip. There are some diodes, also LEDs, light emitting diodes. This particular one, I think it's, this one is voltage converter, voltage regulator. It converts any voltage to 5 volts, and then I think there's another one which converts 5 volts to the 3.3 volts. And then the chip itself, it works on 5 volts, and the pins here, they are also 5 volt pins. And it has digital and analog pins. So the digital pins can be used for output and input. So for output, meaning that they can turn on, so the logic into the chip can turn them on to 5 volts or bring them down to 0 volts. And then the analog pins, they are mostly used for measuring analog input, so they can sense how much voltage is provided to them, and then the chip is converting this voltage into values from 0 to 1023. And with the digital pins, so you can use a trick to make them act as analog output pins, meaning as if they would be changing voltage. But basically, how it is done, it is you are turning them on and off at high frequencies, and by controlling the amount, how long they are on and off at high frequencies, you can make them. You can fake some devices. You can fool some devices into thinking that more or less voltage is provided. So you can dim an LED, or you can drive a motor faster or slower, and so on.
That's PWM?
Yeah, PWM, pulse width modulation.
Okay.
Then this is an ISP header. So with this, you can flash the bootloader of this device in order to use the pins. This one here. Yeah, and I will just show you quickly where you would usually get it. So if you go to Arduino.cc, it's the official Arduino website.
I need an HDMI cable, like, even though it looks the same as a DisplayPort cable, and then it's really just frustrating when you haven't bothered to learn the format. I guess.
Yeah, you just learn it over time. So sometimes I need to refresh it, and it's good that Google exists. Then I can always ask it, and it gives me an image of what I'm looking for. So yeah, and when you have connected to your computer and your Arduino Uno lights up, then you can go to the integrated development environment, And it will start out with this basic skeleton of your sketch, and so some people call it the Arduino language, but actually it's C. So because Arduino development environment is written in the C language, which is a relatively low-level language. This is one level above the assembly language, which is one level above just pure computer code, which is ones and zeros. And it's yeah, and microcontrollers, you know, they have limited complexity, but you can do very complex things anyway. And usually in the microcontroller world, C is going to be the language that that is the most used, and this is the case also with the microcontroller that is used on the Arduino. And the Arduino language is built in a way that it's most of the times it's these two functions to make it easier to do what you want. So the one is called the setup function. It's the first one, and it will contain code what has to be run once at the beginning of the life cycle of the Arduino. So which means when you power it on, then the first thing that is going to be done is going to be defined by the setup function. And then the other one is the loop function, which is going to be continued as long as it's on. So it's going to loop always as fast as it can, like till you disconnect it from the power again. Then in C language there are some rules. So there's void, for example. It means void or nothing, because every function in the C language needs a return type. So this first line, so if we split it in parts, it means, so this first part is the return type of the function, then the second part is the name of the function, then this is the place where you could define some input parameters or arguments for the function, and this opening bracket defines the beginning of the definition of the function. So and in the closing bracket it defines the end of the definition of the function, and it defines also, so before that there should be something that has to be returned, but since we will not necessarily, these two functions, they do not have to return anything, so this is also why the return type of them is void. But the syntax is just asking, even though the function is not returning anything, we have to specify a empty return type, which is void in this case. So for the setup in Arduino, the first thing that we have to do, we have to tell the microcontroller what is going to be the function of the pins, and for that we use a function that is called pin mode, and every function has these opening and closing brackets, pin mode, and we have to specify the number of the pin, and the digital pins are numbered from 0 to 13, so these are altogether 14 pins. And let's say that this is number 13, and we can define it as output. So this capital letter thing, it's called a constant in C language, and it's a predefined constant that defines underlying that actually translates to an underlying value. I think it's 1 or 0, that would tell the program, the microcontroller, to understand, to set this pin to an output mode, so it can be turned to 5 volts or to 0 volts depending on what we want. And then in the loop we can turn it on by using the digital write function. So with digital write we always have to specify the number of the pin first, and then whether we want to turn it on, which is high, or we can use also low for turning it off, but we are going to turn it on first. Then we can use integrated function which is called delay, And here we can specify time in milliseconds, which is 1,000 thousandths of a second. In this case, we can use 1,000 or maybe 500 milliseconds. So half a second, like as a sleep time, as a pause. And then we can use digital write again in order to pull it low like this, and then another pause. And at this point, it's going to reach the end of the function, and what the bootloader or the Arduino library will do, it will jump to the beginning of the loop and repeat this code over and over.
And what are the semicolons?
The semicolons, it's also a language construct. It's more like a rule for a language that every line or every command should end with a semicolon. So some newer languages have avoided this because it's one of the most used errors that beginners make. They forget the semicolon, and then the compiler complains. So let's see. So there's a verify button up here that can be used to verify. First I need to save it somewhere, so I'll save it just on the desktop. Here, and you see that there are things happening on this black part of the editor, and yeah, it's saying also that it's done compiling, and if you see this message, then it's all right, and you know that your code is all right. But let's try to delete one of the semicolons and hit on verify, and yeah, so Arduino software is complaining that it actually expected a semicolon before this bracket, so you can see more detailed information about what happened here, like in the black part. So this is usually the way how you can spot errors like these. We're using the verify button. And then the next button is upload, but in order to use that, you need to make sure that you have connection with a board, and you need to specify the version of your board, because there's no way for Arduino IDE to guess it automatically. I think it could be possible, but they haven't really implemented it. So there is, yeah, Arduino Genuino Uno, and then we have to select the port. In my case, I have connected it somewhere else. I think I'm gonna disconnect the camera for a little bit. This goes here. Here, okay, that's the camera, and I'm going to connect the Arduino. Arduino Uno. It's the second one in the list.
Oh, there.
Yeah, that one.
So first the board and then the port.
Yeah.
I just wanted to try it.
And then, yeah, I'm gonna show it on the screen here as well. Full screen display. Yeah. So, yeah, so now it's switched off because I just disconnected it from my computer. But I'm going to connect it to power supply. So where's the other connector? Ah, here it is. Here you go. Yes. Yeah, now it's on. You see that, we used this digital pin number 13, which actually has a pin connected on the board. So you see this little pin blinking here, little LED. So that's the number 13. But we can also connect LED to the pin. So you see there's a pin number 13 modulation that you can do with digital pins. And yeah, for that I will switch back to the screen.
It worked for me before. Now I have no hardware, so I'm pretty hardware is the nearest one, right? So it does work. There's just something missing. Don't worry.
Yeah, here we go. And for the PWM to work, so we can specify the pin mode as output, so we can leave the setup function as it is now, and we can use command or a function that is called analog write, and I think it is going to accept values from 0 to 255. So first we have to tell it the number of the pin, and then we have to specify the value, which could be 115 in this case. But in order to make it a bit more interesting, we are going to use a loop, like another concept of programming, which is really useful but not so easy to understand for beginners, but this is more like a demonstration of what is possible. So I'm going to use a for, or maybe a while loop. Yeah, while loop. But before that, I'm going to make a variable, so like an integer variable counter, which I'm going to set to 0. So this is a way how you can make new variables in programming language. So in C language specifically. So this is telling the compiler the type of the variable that you want to create, which the compiler actually uses to reserve some amount of memory in the computer's memory. And then you give it a name, so you can use it in your code after this line. In our case, it's going to be the counter, and we set the value to 0, and then we use the while loop. So while, and for the while while loop, you use parentheses to define what has to be checked against. So while counter is less than 256, then we are going to analog write this to the value of counter, and we are going to increase the counter. And then the while loop is going to end. So every time the while loop is going to reach this end, this closing bracket, it's going to check whether the counter is still less than 256. And if it's still less than 256, it's going to run this code. So it's going to set the pin 13 to another value, and it's going to increase the value of the counter by 1. And then it's going to check again, and it's going to run until it's going to loop until the value of counter is going to be less than 256. And then after this while loop, so we actually can make a copy of the same. We're going to check whether the counter is still more than 0. And instead of adding 1, we are going to subtract 1. And we should add one more thing, which is a delay after each of these. So delay, I'll set it to 50, and the delay should be here as well. 50, like this. And let's check it. Let's verify.
Yeah. No, but that's just home to CAD. I don't know.
So compiled, and I'll try to upload it once more. Disconnect the camera.
Is that CAD?
Yeah, I installed it, but I'm not sure if I uninstalled it.
Yeah. After that, everything's good.
Yeah. So now. Okay, slowly dimming, so we could actually.
Now I lost it. Yeah. Oh, I can try it, but it's weird because it was just working before.
So I changed the delay to 5. Yeah, but let's go over the code one more time. So what we are doing here, I also changed the pin to pin number 11 because apparently, yeah, there are only like this PWM or the brightness, yeah, this pulse width modulation, it works only with the pins that are marked as PWMs. But I think you can use also a library that would let you to use the other pins as PWMs. I think that the chip that Arduino uses, it has an integrated pulse width modulation functionality. You don't have to add extra things to it, but then if you want to use other pins, you have to do it on your own or using a library in code. So yeah, I changed, so I set the pin 11 on the board to function as an output pin, so I can send commands on and off or like values to it. Then here I'm starting to define the loop function, so by specifying that it doesn't have a return type, its name is loop, it doesn't have any parameters, and this starts the definition of the body of the function. Then I'm creating a variable of the type integer. So integer means just a whole number, or is it like a real number? So it can be in the range from minus 11 million or something up to 11 million and plus. So there's also unsigned integer, which is just the numbers, possible numbers in only on the positive side. So basically, if you shift the whole scope by the maximum possible number, like by 11 million, then it's going to be twice the size, but only positive numbers. I think that normally this in the int type is 16 bits, and if you take number 2 and then you power it by 16, then you have altogether 65,000, or was it 32? Wait a minute.
But it's a lot of numbers. Do you need that many different? Like, do you need more than 100?
So integer usually is 2 or 4 bytes. So 1 byte is 8 bits, 2 bytes is 16. So basically 2 in the power of 16, it's 65,000. So which means if it's 65,000, then if you divide 65,000 by 2, you get the maximum number for an integer is 32,768. So with Google, yeah, can help you on this. So which is, yeah, you see here that it goes from minus 32,768 to 32. So if you're using larger numbers with the integer data type, then be careful. There's also like 8 other data types. So this is an example of unsigned integer. So it can just be the whole from 0 to maximum to 65,000. So it's just without the sign, without a minus sign. So yeah, we are defining a data type. So the computer allocates like 2 bytes of memory for this data to kind of translate the number that we want into this byte data in the memory, and then we are giving it a name that we can reuse in the code later. And then with this equal sign, we are assigning a value, and we are assigning a value 0. And this is just syntax, so the semicolon. You had a question?
Well, I don't know. Like, because the value is not always 0, but why it's now 0? Yeah, the counter value.
Because like you have to start with something.
Yep.
So
you
and
just then like 1, 2, 3, 4, like if you make a lot. Well, I don't know. Maybe. Well, it doesn't matter.
I mean, that's what the code there is. Counter equals counter plus 1, but it starts at 0. So it starts where
like,
counter is 0.
Yeah.
Counter is 0, where you initiate it at 0. Then, yeah, down there, there's that code counter equals counter, which is already up there, plus 1. So it goes from 0 to 1, then to like every time it loops, then it, when it gets to the end of the code, it goes back to the beginning of the loop and then does, right?
Yeah, so there are 2 loops. No, there are 2 loops. So there's one bigger loop. It's just it's being run by the Arduino as fast as it can. So it's more like a place, more like a block of code that is being run. That the Arduino itself it repeats, and then so this while it's also a loop, but it's a bit different.
Something.
Yeah, so this is more like with this loop you can check so it's called while because you specify the condition, so while it runs, while it loops. So basically it loops while the counter is less than 256. So at the beginning it's 0, so it's obviously less. So and this it runs until, so it basically executes all these 3 lines. It runs these 3 lines after that. So it's setting the pin 11 to the value of counter, which at that point is 0. So it's basically switching it off, and then it's increasing the number of the counter by 1. Then it becomes 1, and then it waits for 5 milliseconds. Then it reaches the end, and then it basically asks the same question: is it still less than 256? And it still is, as it's 1. And then it through this cycle it becomes 2, and it just happens really, really fast until it asks the question again, and the counter is actually 256, and then it's okay. Now we can exit the loop, and then it goes forward. So the next line, next line, next line, and there's another while loop which asks, hey, but now is the counter actually larger than 0? And since it's, and so we go. Yeah. And then we upload the code, and it looks like this. I will connect the camera in order. To break, but still, one probably should add a resistor in this case. But for a demo, it's fine just like that. So yeah, this is a sample scenario. We could also, like, instead of LEDs, we can use speakers. It's giving us sound. Yeah, you can see that it changes, like the frequency changes. This is basically how the LED is controlled. So it's just high frequency sound that represents the on and off values of. the LED being turned on and off. Yeah, this is a bit annoying. Yeah, and yeah, that's about the basics. So then I wanted to show you a few other things that are possible with electronics. So for example, during the Fab Academy, people are expected to make a circuit board that look like this. And in order to make them, you use specialized software, such as KiCad or Eagle, and then you place the electronic components there, and then you transform the electronic schematic into something that looks like this, and then you use etching or precision milling in order to get it out in this format, so kind of to eat away the copper that is not needed, and then you drill the holes and you solder the actual components on top of this, so you get something like the Arduino at the end. So you see here you have all the components soldered on it already. Yeah, this is another example. This is etched, right?
Yeah, I think so.
Yeah. So with etching, you can actually get higher precision. So, but there are like quite toxic chemicals involved. So
Like
if you, yeah, so like this. And I'm going to show you a demo with a software that's called Eagle. So if you, it's now owned by Autodesk. So.
Nothing can happen because you told pin 11 to do something, but nothing's plugged into pin 11. Yeah? Yeah. But this is still
Yeah, so you can download it here for Windows, Mac, and also Linux apparently. So which is really that's a new feature. I think it was not existing for Linux systems. So it's with a free version you can get I think up to 2 layers and 2 schematic sheets, and you can make a board up to size. So like 10 by 8 centimeters, but it's enough for simple electronic projects. And when you download it and you open it, you'll be presented with a screen like this. And on the left side you will have projects. Here you'll be able to start a new project. I'll just call it demo, and for each project you can create a schematic, a board, or a library. In our case, I'm just going to start with a schematic, and for the schematic you have a specific workspace. So it looks similar as the other computer-aided design programs out there. So it usually has. So they usually have like a toolbar with all kinds of tools. So these tools are specific to electronics design, and the main part here is the add part item, add part function. So you click on that, and you'll be presented with a. At first, it's going to look quite complicated, but you're going to be presented with a list of libraries that you have installed. And in my case, I have some SparkFun things, so like IC power, yeah, I don't know, like battery. But usually a circuit is going to start with basic power definitions. So you need to have so there's a library, like integrated library that is called power, I think, or you can use the search and search for VCCI supply. Yeah, supply 1. So you need to put so this is usually for plus, and this is how you place it. You just click on the area somewhere, and then you hit escape. I think I can now enable this one. And then the other thing that you always need is going to be ground, like G and D. Supply 1 G and D. Okay, let's put this here. I'll hit escape one more time and twice to close the dialog. And then this tool, so it's the move tool, so you can click on that in order to click on the part, and then so it doesn't work really exactly as Illustrator or Fusion. So you first have to click on the part, itself, and then you can move it around, and then you have to do another click in order to place it somewhere. And then the same with the ground. And in between these two, you can make your circuit, and you're just going to make like a simple LED circuit here. And in order to make an LED circuit, we need to add an LED. So we go to this add part dialog again, and we look for LED. And let's see, so there are just too many options. Let's choose something from Adafruit, for example. So, and for each component you will also have usually the schematic symbol, and then also the part diagram, or how it's going to look on the board that you are going to produce. So you get a footprint. This is called a footprint. And this, for example, is LED 3mm. I think this is an LED with 3mm spacing between the terminals. This is a 5mm one. Or, no, this is...
So they're like SMD?
No,
components?
these are through-hole components.
Ah.
But it looks like that it's like a LED like the size of it is 5mm. The diameter of this is 5. And then this one is just 3mm. Yeah, kind of the housing of it, it's 3mm.
Yeah, like the diameter of the LED?
Yeah, of the LED itself, it looks like.
Yeah.
So these are SMD. So you see, when you see these squarey parts, so the squarey
SMD
connectors, it's surface mount.
design or surface mount?
Surface mount, dude.
What? Is in the component.
So, like, it's these ones that are on the really small ones, right? Like the LED, right? The LED that was blinking.
Yeah.
And it's just on the surface.
Like attached.
Yeah.
Somehow, like.
But then through hole, which you was mentioning before, it's
Like this.
yeah,
that goes.
it's going through the hole.
Yeah, so these are the so usually nowadays when companies release new components, they skip the through-hole ones. Like the SMD is the standard, and this is why it's useful to learn like etching and milling, so PCB production, because this is the way how you can get the latest components in case you need them. Yeah, the through holes, you can still get the basic parts in order to nail the basics of electronics, but then in order to make something more serious, you rather switch to SMD. And yeah, it just needs like a few times of going through the process, and then you're getting more familiar with it and more comfortable with it every time you do it, obviously. So yeah, let's choose this 5mm one, because I think this is, if not 5, then even more, the one that we used before. And hit OK. And here you can see, yeah, there's kind of a little arrow. And so the line is usually defining the ground. And so it points in the direction of where the current flows. So if you remember the presentation at the beginning, that usually, like in these diagrams, it flows from plus to minus. So this VCC is plus, and then the GND is minus. And we need another component. Let's add a resistor. And let's try to choose it from some similar libraries. So the Adafruit, I wonder why they.
There's flip-flop res and American symbol.
Well, this
That's
is good enough.
easy.
Yeah, but this is not it.
No, wait.
No, this
that's
is through hole.
That's through hole.
Or it's both. Oh.
Yeah.
Yeah, there are all kinds of. Here are. Yeah, let's. Okay, Adafruit. Yeah, let's use that.
The drumming session has started.
What is that?
It's time for African drumming.
And then you can use right click in order to rotate it around in case you need to position it. Is it delete or was it something else? Why don't I see it? Can just I can right click and delete, but there was a special tool for it. You can just type delete and then it used to be like a like a little garbage can that you can click on, but here it is. Yeah, this one. Delete. And you can delete all those or the ones you don't like. And you can redo them again like this. And then, for example, you also need so these symbols, this VCC and GND, these are just symbols. They are not any components. If you're producing a board where there is going to be connection for the plus and minus, then you need to add this connection as well.
The LED there though, it's got a plus on the lower side. So is it the wrong way around maybe?
No, it's just showing the origin of it. So there's the label. There's the origin of the label that you have here. It's also for the resistor here. Yeah, and then you need to add header. So, and there's all kinds of connectors. So SparkFun has some, and yeah, let's use something from these. 1x1. They don't have like 1 times 2 for some reason, but we could just add them separately. So let's say this one here, another one here, and let's add this net again in order to connect this to the plus and then this to the minus like this. And then we can give names to the components by using the name tool, and this let's call the power plus, and let's call this one power minus. And then we can give names also to the components themselves. Resistor 1 and LED 1 is okay. And then for the resistors we can also give values. So here's another tool that's called the value. So let's say this is going to be 1K, and the LED, I don't know, for the power, so 5 volts, and here's 0 volts, like this. And at this point, so we have a full circuit, and we can actually switch over to designing our board. And for that, you have this icon here. It's gonna ask you whether you want to create a new board from the schematic, and say yes. and it's gonna bring you into the board view. It's kind of this mouse effect is a bit annoying. Where you see that all the and we can also move these dimensions around like this. And yeah, and our board is ready. And then there are layers in Eagle, and the components themselves you will see on the top layer like this. Then there are pads that are visible, and so then there are these wires. No, it's not ready, sorry. So we need to use another tool which is called the root tool. So this one, in order to create solder, so these copper joints. So, and we need to set a width. So for example, if we are doing it with milling, then we need to set a certain width of the traces, and so the value here is in thousandths of inch. So which is weird. If you enter, I wonder if you enter it in millimeters. So yeah, you can enter it in millimeters also, and it's going to automatically convert them to these thousandths of inches. So 0.4 millimeters translate to 15.7 mils. But yeah, you would use usually 16. And then there's another thing in the design rules, but I'm not going to talk about that now. And then you just click and do the routing manually. There are some automatic tools for that, but usually you end up doing it manually anyway. Yeah, and now it's there, so now it's connected. And then at this point, so if you would want to mill it with our machines, then what you should do, you should export PNG image from this, but you shouldn't export everything that you see here. You should only export the pads and the traces that you see in between the components. So what do? You go to layer settings here, and you hide everything, and you just show the top. It's rather weird. Yeah, the top and the pads like this, and maybe no, even not the dimension. And then you hit OK, and then you go to File, Export Image, and you browse where you want to save it. So it's gonna be Eagle Demo Traces. Save. You have to set it to monochrome and 500 dpi and the full area, and then you hit OK. And when you go, so Eagle has a bug it usually creates that is made by MIT Center of Bits and Atoms in order to in order to generate toolpaths for many different milling machines. So it's kind of 2 times bigger image. So you should always check the dimensions here. So if I enter 1000, then it shrinks it down to 1 centimeter. So basically, is it that our design is only 1 centimeter wide? So if we add a dimension from here to here, it's actually 17. It actually could be it. In this case, it didn't make a mistake for some reason. So it's 2 centimeters by 2 centimeters. So 500. And for the output format, you need to select roll and mill. And for the process, select traces. And for the machine, so here we have the MDX40 working. You have to select this, set this to 0 and 0. And then you have to hit calculate. It's going to calculate the tool paths. So these blue lines is where the drilling bit is going to go. So there are other small things to it. So you usually should know the diameter of the drilling tool that you are, of the milling tool that you are going to use, and the cut depth might be different. So